Hey guys, so I just wanted to go over this worksheet from last week. So there were a number of mistakes that I saw, especially around continuity and whether or not the function was defined at the point and all kinds of things. So I just want to clear up those issues. Let's start with number one. We're being asked to do a lot of different things in these problems. First of all, we're sort of being asked, you know, does the limit exist or not, right? So we have to try to evaluate this limit. And you know that if you're trying to evaluate a limit, the first thing you should do is just try plugging the number in. So you should just try plugging 1 into this function. I'll skip the arithmetic. If you plug 1 into this function, you get 0 over 0. What does that tell us? Well, it doesn't tell us the value of the limit. As you know, we have to rewrite this expression and try again to find the value of the limit. But it actually does tell us something. This tells us that this function, which I'll call f, is undefined at x equals 1. Right? This function is undefined at x equals 1 because we just tried plugging in 1 and we got an undefined expression, 0 over 0. Okay, so f is undefined at x equals 1. What I'm going to do is just sort of note this information, highlight it, and we'll take another look at it in a moment. We'll come back to what this implies for the rest of the problem in a second. But let's continue with trying to evaluate this limit. As you know, we have to try to simplify this thing, rewrite it if we can, and try again. So of course, we can factor the top and bottom. The top factors is x plus 3 times x minus 1, and the bottom factors as x plus 1 times x minus 1. Those two x minus 1s cancel, and that leaves me with x plus 3 over x plus 1, which now, if I try plugging in 1, I get 4 over 2, which of course is just 2. Great. So the limit does exist, and it's 2, right? The value of this limit is 2. So the limit does exist, and it's 2. Great. So we can go over here. They want us to, right here, they want us to say whether the limit exists or not. Well, it does, as we just saw. And it's 2. Cool. But now they want us to address whether the function is continuous at the point or not. And if it's not continuous, describe the kind of discontinuity. In other words, whether it's a hole or a vertical asymptote. In order to decide whether it's continuous or not, you really have to know the definition of continuity. So let's recall what that is. Being continuous at x equals 1 means this. That's the continuity equation that we introduced 2-3 weeks ago. The limit as x approaches 1 has to be equal to the value at 1. All right, that's what it means to be continuous at x equals 1. And if you remember, we really emphasized that in order for this equation to be true, in other words, for the function to be continuous at the point, several things have to go right. Several things have to be true. First of all, this expression here has to be defined. The limit has to be defined, right? And in this case, it is. We just saw that the limit is defined. The limit does exist. It's 2, okay? Secondly, this expression has to be defined, right? In this case, that's not true. Remember what this is. This is the value of the function at 1. And if you plug in 1, you get 0 over 0. So f is not defined at 1. Therefore, this expression is undefined, which means this equation cannot possibly be true, which means the function is not continuous at x equals 1. So since f of 1 undefined, the function is not continuous at x equals 1. Okay? So a lot of people said that this function was continuous, I think because they saw that the limit existed and they're like, oh, if the limit exists, that means it's continuous. No. Remember that being continuous at x equals 1 means that this equation is true. And for this equation to be true, a bunch of stuff has to happen. The limit has to exist, which it does. And the value of the function also has to exist, which it does not. right? The function is not defined at 1. And even if those two things exist, they have to agree, right? There's a bunch of stuff that has to happen. In this case, the limit exists, but the value at the point does not. So therefore, it's not continuous at x equals 1, okay? Now, that leads us to the question, so we can say over here, it's not continuous. But now we have to decide, like, is it a vertical asymptote or is it a hole? As I think you've been told, you only get a vertical asymptote if you obtain a non-zero number over 0 when you plug in the value, okay? Let me just be clear. In this case, we plugged in 1, and what did we get? 0 over 0, okay? On the other hand, let's go down to number 3. I'm sort of getting ahead of myself, but it'll be a good example. If I plug -5 into this expression, what do I get? I get -8 over 0. That is a non-zero number over 0. That means you have a vertical asymptote. Non-zero over 0 means vertical asymptote. And that is the only time you will have a vertical asymptote, okay? I saw people sort of saying that lots of functions had vertical asymptotes. No. You only have a vertical asymptote if, when you plug in the number, you get a non-zero number over 0. Okay, that's the only time. If you get 0 over 0, that just means you need to rewrite your expression and try again, okay? Typically, this means a hole. A non-zero number over 0 indicates a vertical asymptote. The reason for that is basically this fraction is a ratio. It's a comparison, okay? And the numerator is infinitely larger than the denominator, right? Like 8 is not 10 times bigger than 0. It's not 100 times bigger than 0. It's not 1,000 times bigger than 0. It's infinitely many times larger than 0. So when you have a non-zero number over 0, that's indicating some kind of infinity. And that's the only time that you have a vertical asymptote. Non-zero over 0. Okay? At any rate, I claim that this is a hole, and I really want to make it clear why it's a hole. If we go over to the graph of the function, I have it right here. This is what it looks like. And here's what's happening at x equals 1. You can see I've put a hole there. Now, why does this picture match the information that's been given here? Well, for one thing, the function is not defined at x equals 1, which means there has to be some kind of a gap here, right? Like I can't fill this in because that would be implying that the function is defined at x equals 1, and it's not. However, the limit does exist, right? Even though the function is not defined at x equals 1, nonetheless, the limit as x approaches 1 does exist, and it's 2. And that's what you're seeing here, okay? Yes, the function is not defined at 1 on the nose, but as you approach 1 from either side, the value of the function is approaching 2, as you can see right here. And that's what we saw in the calculation, okay? So, short summary, guys. If the limit exists, but the function is undefined at the point, that means you've got a hole, okay? That's what a hole really is. The limit exists, like the value of the function is approaching something, but the function's undefined at the point, all right? So this is a hole. And the truth is that most of these problems in this worksheet are exactly the same way. Most of them are holes, all right? Let's go through them quickly. So number 2, again, you should just try plugging in the number, right? Sometimes you get lucky. And in this case, you do. If you plug in 3, you get square root of, well, 3 plus 1 is 4, and then 3 squared plus 1 is 10. So that gives you 2/10 or 1/5. So that is just a regular number, right? That's telling us that this function f is defined at x equals 3. It's defined at x equals 3, and it's 1/5, okay? So actually, this function is continuous at 1/5, or excuse me, at 3, right? It's defined there. the value of the function is 1/5, and the limit as x approaches 3 is 1/5, right? As we've said, if you're trying to evaluate a limit and you just plug in the number and you get something reasonable, that's the value of the limit. So as we're seeing, the original function itself is defined at 3, and the limit also exists at 3, right? So yeah, the limit exists. It's 1/5. That's also the value of the function at 3, okay? So this function is continuous. Why? Basically because the limit, let me just adjust this. The reason why is the limit as x approaches 3 is the same as the value of the function at 3, right? Like, this function is defined at 3, and its value is 1/5. So, okay, this thing is 1/5. And also, the limit as x approaches 3 is 1/5, okay? So this function is continuous. This is the only continuous problem, or the only continuous function in out of all of them, okay? Going to number 3, we saw this is a vertical asymptote because you get a non-zero over 0. We wanted you to evaluate, like, the vertical asymptote, like, in other words, determine whether the graph is going to positive infinity or negative infinity from either side. How do you do that without graphing it? Here's what you do. You plug in a value just to the left of this number here and a value just to the right of this number here, and you see what you get. So to see what I mean by that, let's try evaluating f at negative 5.01. That is a number just to the left of negative 5. If I plug in negative 5.01, I have negative 5.01 minus 3 over negative 5.01 plus 5. That gives me negative 8.01 over negative 0.01. The negatives cancel, and dividing by 0.01 is like multiplying by 100. So you get positive 801. Okay, so the value of the function just to the left of negative 5 is a giant positive number. That's telling you that as you approach negative 5 from the left, the function's going to positive infinity. Okay? I can represent that using notation by writing the limit as x approaches negative 5 from the left is equal to positive infinity. Now, to see what's happening on the other side of the vertical asymptote, I plug in a value just to the right of negative 5, like negative 4.99. If I do that, I get negative 4.99 minus 3 over negative 4.99 plus 5, which gives me negative 7.99 over, I think, positive 0.01. This gives you negative 799. So that's a giant negative number, right? So what that's telling me is just to the right of negative 5, the value of my function is a really, really big negative number. That's telling me that the limit, as you approach negative 5 from the right, is negative infinity. So as you approach negative 5 from the right, that's negative infinity. Okay? So what we would say about this limit, the limit doesn't exist, right? This limit is not approaching any particular number, like, say, 1/5 or 2. It's just blowing up, right? So it doesn't exist. And in particular, we write does not exist plus or minus infinity, indicating that on one side of the vertical asymptote, the function goes to positive infinity, and on the other, it goes to negative infinity. And if we graph this, you see exactly what I mean. This is, here's what the graph looks like. Okay, and here's negative 5. So you can see that as you approach negative 5 from the left, the function's going to positive infinity. As you approach negative 5 from the right, the function's going to negative infinity. So yeah, the limit doesn't exist, right? As you approach negative 5, the value of the function isn't converging to anything. It's not converging to 2 or settling down to a number like 3. It's just blowing up, okay? Now, is the function continuous or not? It's definitely not continuous, okay? Because the function's undefined at the point, and the limit doesn't exist. Like, this function's really not continuous, right? It's not defined at the point, like it's not defined at -5. That already is enough to say that it's not continuous. But even the limit doesn't even exist, right? Like, both sides of the continuity equation don't exist. The continuity equation, let's remember, for this would be, let's see, so to be continuous at -5 would mean this equation is true, right? So to be continuous at -5 means this. Well, neither side of this equation is defined, right? Like, the function's not defined at -5, so already we can say it's not continuous, but this side isn't defined either. Like, the limit doesn't exist. So neither side of the continuity equation is defined. So it's definitely not continuous. Now, as far as what kind of discontinuity, it's a vertical asymptote, right? So not continuous, and it's a vertical asymptote. Okay. The rest of these we can do really quickly because they're all pretty much the same. This one, you can factor. You'll see that the limit does exist, but the function's undefined at the point, right? So like f of -4, if you plug it in, you get 0/0. Therefore, the function is not defined at the point, which means that the function is not continuous, right? But the limit does exist. The limit does exist. You can factor this and you get some number. I forget exactly what you get, but you get some number, right? So the two-sided limit exists, but the function is undefined at the point. That's a hole. It's just like number 1, just like it. Number 5, exactly the same thing. If you plug in the number, if you plug in 5, you get 0/0, which is undefined. So the function is not defined at 5, which means it's not continuous there. But the limit does exist, right? If you multiply this out and cancel common factors, you do see that the limit exists. So once again, the limit exists, but the function is undefined at the point. That's a hole, right? That's really like, I mean, just to be clear, that is really the characteristic of having a hole, right? If you have a hole, what that means is the function is undefined at the point, but the limit does exist, which is what you're seeing here, right? There's a little gap, so the function is not defined at this point, at x = 1, and yet the limit does exist. As you approach 1, the value of the function is converging to a certain value. Okay, so holes are really characterized by function is undefined at the point, but the limit exists. Number 6 here is another vertical asymptote. And how do I know? Because when you plug in the number 2, you get 3/0, a non-zero number over 0. Non-zero over 0 means vertical asymptote. So it's definitely not continuous because the function's undefined, at the point. But we need to analyze both sides of the vertical asymptote, like what's happening as you approach 2 from the left and the right. What you can do is, just like before, plug in a number just to the left of 2 and a number just to the right of 2 and see what you get. If you plug in a number just to the left of 2, like 1.99, you have 1.99 plus 1 over 1.99 minus 2 squared. So that's going to be 2.99 over, I guess, -0.1 squared, which is 2.99 over +0.01, which is like 299. So that's a big positive value. So as you approach from the left, the function's going to positive infinity. What if you approach from the right? Well, plug in a value just to the right of 2, like 2.01. I'll skip the arithmetic. You also get a big positive number. Okay, so it's going to positive infinity in both directions. So, the limit doesn't exist, and it's giving us positive infinity in both directions. Okay. And then finally, number 7. Number 7 is another whole. You know, if you plug in 0, you get 0 over 0, so the function's not defined there. But the limit does exist. A lot of people had trouble with this one. You have to multiply top and bottom by the conjugate. Okay? So I'll just remind you how that goes. So I'm going to multiply top and bottom by the conjugate of this guy right here. The conjugate of that expression is 1 plus the square root blah, blah, blah. So I'm just going to multiply both top and bottom by 1 plus the square root of x squared plus 1. 1 plus the square root of x squared plus 1. Now, what do I get? In the numerator, something nice happens, right? If you multiply all this out, the square roots will kind of disappear. That's because this is the product of a sum and a difference. It's like a plus b and a minus b. That's always going to give you a squared minus b squared. So you'll get 1 squared, which is just 1, minus this expression squared, which when you square that expression, the root just goes away. Notice that, you know, you wind up subtracting this entire expression squared. So like this minus sign hits both those terms. A lot of people miss that. In the denominator, you shouldn't distribute anything. Don't distribute. Okay, like every time you do one of these conjugate problems, you're going to have the product of a sum and a difference somewhere, either up top or down below. The product of a sum and a difference should be multiplied out because it gives you something nice. It gives you the difference of two squares. But the other part of the fraction, just leave it in factored form. Don't distribute this x squared. And you'll see why. Because in the numerator, you can see that if I distribute the minus sign to these two terms, the 1's are going to cancel, and the whole numerator just becomes negative x squared. In the denominator, I'm not changing anything. I'm just copying, right? I'm not going to distribute that, that x squared. And now you can see it's good that I didn't distribute the x squared, because now you can see that the x squareds cancel, right? If you had distributed the x squared, then it would be a lot less obvious that they cancel, but here it's pretty clear, right? The x squareds cancel, so that leaves you with negative 1 over the 1 plus the square root of x squared plus 1. And now this is something that you can actually work with. This is simplified. If you replace the x with 0 now, you get something reasonable. You get negative 1 over 1 plus square root of, 0 plus 1, which that whole thing simplifies to negative 1/2. Okay. Okay, so I hope that was helpful, guys. Have a good week.